All right, good morning. Good morning to everyone, and welcome to day 2 of the CitrusSprayEx application workshop. Again, my name is Dr. Peter Akunlabi, Assistant Cooperative Extension Specialist in Agricultural Application Engineering with the University of California Division of Agriculture and Natural Resources. And I'm located at the Kenya Agricultural Research and Extension Center in Palia, California. And yesterday we started this workshop. Today is day 2. We'll be completing today. And I want to go over it, that this workshop is part of our project that is sponsored by the Department of Pesticide Regulation, the DPR. And the title of our project is Dissemination and Training for Citrus Spray Application Expert System Adoption in California. And my other key persons on the project are my colleagues, Dr. Beth Grafton-Cardwell, Director at the Lincoln Research and Extension Center, and Dr. Greg Duhan, Cooperative Extension Area Citrus Advisor for Tulare County. And I would also, again, like to acknowledge the support of the ANR Program Support Unit for their support in organizing and running this workshop. Yesterday turned out to be a good day for us going through day 1. And I'm looking forward to a great day as well for day 2. Again, as a start, I would want to ask that you provide your full name and your location on the chat, and let's just use that as just our initial interaction. So please go ahead, enter your name, your full name, and then your location on the chat, and then we can move on to the rest of today's activities. Okay, a few seconds and then we would move on. Thank you very much for coming back to today. And here is our agenda for today. We have this welcome and introductions going on right now, and it's going to run shorter than is on the agenda. But once we are done with the initial welcome and introductions, we would move on to do a hands-on demonstration for spray application evaluation. Yesterday, we looked at we did a hands-on demonstration for spray planning, and we looked at sprayer calibration and also spray application timing. Today, we are dwelling on the spray application evaluation. And you must have received your the handout for the hands-on part. So we would run from 9:15 and break at 11 o'clock. I am hoping that we would have the time will be sufficient to go through everything that I have outlined. And if we need more time, hopefully we would not be needing more time, but if we need more time, I would assess it and see how we would go about it. But hopefully we would not need more time to complete what has been lined out for the hands-on. So from break, we would get into the wrap-up discussion, questions and answers. And during this time, I would actually discuss the hands-on part, whether I'll go through and discuss part of the results that I am expecting to have. And so during that time too, if you have questions or you have other things that you think we can discuss in relation to the topic of spray application and improving spray application and calibration and anything related to spray application that you want us to talk about, we can get into discussing it as appropriate within the time that we would have to round up. And then during that time to would spend, I would love to have some feedback from you in terms of your experience of the application. And I would stress again that the CitrusSprayEx expert system that you're working with, this is the initial form that we have it, and in the long run through this project, we are working on developing a new system that would go beyond Citrus. So the improvements we are looking at incorporating, not just within this project, but beyond the project, is adding on other crops, other tree crops, and then also improving the data collection for other sprayer types, and then factoring those in the design. So maybe a user can select specific or select inputs that are more specific to their application. And we believe that as we incorporate all the feedback that we are going to get from interacting with people on the project, we would be able to come out with a system that would be more useful and more applicable to our day in, day out spray application decision making. So with that said, let's get on with a hands-on demonstration. And if you don't have your application up right now, I would say go ahead and get it on, because we will be running through the application shortly. Okay, so let me give a quick overview of, let me start by giving a quick overview of the spray evaluation part of the expert system. So this is the welcome screen that you see anytime you are opening the program for the first time. And then yesterday we looked at the spray planning part. Today we are dwelling on the spray evaluation part. So when you click on that button, this is what you find. And so everything that you do in relation to that aspect, you would find it on the screen. There are no additional screens like we had in the spray planning parts. Okay, and we can see there are several inputs that are required for the user to make before running a simulation. The inputs are broken down into application parameters, tree characteristics here, and we have orchard condition, and then weather parameters. So a user would make all these entries. The sprayer make, this is by default, it's a rear sprayer that we used in developing this In going forward, we plan to improve this part by collecting data from other specific sprayer types, and then populating that data in the next version of the expert system that we are working on. So the air outlet dimensions are also based on the measurements from the sprayer we used to develop the data. So airflow rate, this is this is variable. Inputs that you can put there. This is the rated airflow rate of the sprayer. And nozzle type, this is by default set to ask for upper nozzle and lower nozzle. So meaning that you can use this for a non-uniform application, but for uniform, what it means is that you select the same nozzle for both upper and lower nozzle. And the number of open nozzles, these are all the nozzles that you would be using. So if you have a sprayer that has more than this or less than this, that is the number that would be the number that you would be using, not the entire set of nozzles on the sprayer, but the nozzles that are actually going to be spraying, the number of nozzles that are actually going to be spraying. So in this example here, as shown here, this is 12, upper nozzles 36, lower nozzles 36. So in that case, for uniform application, it doesn't really matter whether it's the upper is, even if we change this to maybe 8 upper and then 4 lower, because if we select the same nozzle, then it doesn't really matter. But if you select different nozzles, and if you select different nozzles, then the computations will be based on the fact that the upper nozzles are made up of so and so number of nozzles, and the type of nozzle is this one, and then so the calculations will be based on that. And then operating pressure is also an input required here. Ground speed is an input required here. Now, in terms of the ground speed, this you can set it. You can just put it here, or if you need to do what do you call it, a calibration before putting it here, then you can go back to the spray planning, and based on the you can go to the spray planning and then determine and then use that to help you determine the ground speed of the sprayer, and then you would put that one here, what you have worked on or what you have determined over here. But if you have a desired ground speed, you would just put that here as appropriate. And then tree characteristics. So you have the tree height, you have skirt height. That is the base of the canopy, the space between the ground and the base of the canopy. And then you have the canopy diameter set here. Now, this particular the calculations in this expert system are based on single trees. So at this point, we have not considered hedge rows. So it's one of the improvements that we would need to put into the new design of the expert system, so that so that a user can either select single standing trees or can select hedge rows, so that the computations can be varied or suited to that specific design. And then foliage density, we have low, medium, and high foliage density. These are set ranks that we developed based on measurements we took from a few different types of citrus trees. Later on, as we develop it further, we would need to develop a means by which a user can actually measure the foliage density, maybe measure it for a few trees and then find an average, and then based on that can find an actual ranking. Otherwise, at this point, foliage density is based on just a visual assessment, and if you're using this and you feel that based on your knowledge of the ranges, a particular the canopy is generally or averagely low density, that is what you put there. If it's medium density, that is what you would put there, and high density, that would be what you would put there. So there would need to be some improvement in how these are expressed so that we can have a more specific outcome. But at this point, you just select low, medium, or high, and the calculations should be based on the values that were determined and are having used in the model. So for orchard condition, we have number of trees per row, we have number of rows. So this computation this computation would be done for an entire field as defined by the number of rows and number of trees. And then the tree spacing would have to be such that the canopy diameter would always be, or the tree spacing is limited on the lower end by canopy diameter, meaning that the tree spacing cannot be less than the canopy diameter. At the minimum, tree spacing can be equal to canopy diameter, so that it's considered that the canopies are touching, and this is a limitation because we have not considered hedgerows. But once we consider hedgerows, then we can consider that the trees the canopy can be a continuous canopy, as we know in hedgerows. And then the row spacing is also limited by the size of it's limited by the size of the sprayer, and then the canopy diameter. So at some point there wouldn't be enough space, if that means that at some minimum point there wouldn't be enough space for the sprayer to fit in, and when that point is determined, the system will notify you that the selected row spacing would lead to insufficient space for the sprayer to pass through. So all those bells and whistles have been factored in so that we can use appropriate values, but these would still be improved in the long term. And so because this is considering number of trees and number of rows, looking at the whole block, this also looks at whether there are some missing trees within that. So the computation should be based on the aggregate characteristics of the orchard. So if you have some missing trees, then that would tend to increase drift, because this is also at this point considering a conventional sprayer which does not have the ability to open and shut nozzles on the go like you will have in some variable rate sprayers. And then we have weather parameters. These are the three weather parameters that are considered here: temperature, relative humidity, wind speed. So again, some limits have been put in here to reduce the chances of a user putting in wrong values, but the range is reasonable, and you can explore that as you interact with it. These other variables, these are based on, these variables are what do you call it, derived from the inputs that are made here. I have noticed that the output per site computation, what is displayed here, is not the correct one due to a factor that was used in for the display. But it does not, what is displayed here does not affect the computation. So it's been fixed. We've identified it and fixed it, but it wouldn't be showing in the version that you have, what do you call it, that you have downloaded. And the factor was due to improper display. We had used it. We had converted from metric to English units, and did not change one of the factors appropriately. But that only affects the display. It does not affect the computation. So the total volume applied would be what it's supposed to be. And the total area covered is also provided. The most important variable in this list is the application rate we talked about yesterday. So this would be recorded here. And then the number of trees sprayed together would be based on your number of trees and row information. So once we have all these inputs in place, you click on simulate, and then to run through the computations and then yield canopy deposition, ground fallout, and spray rate. And I would say canopy deposition, all of these calculations are based on the entire orchard condition, So it is percentage of the total volume applied, which you find here. So the total volume applied, this will give the percentage of that. So at this point, this is not displaying exactly how much. So if you want to know the actual volume that was captured by all the canopies, or estimated to be captured by all the canopies, then you have to multiply the proportion or find the percentage of the total volume applied to do that. So we can draw, some inferences from here and do further computations to actually find what we are looking for. But the outputs are all just the percentages. We have ground fallout. This would be computation for direct ground fallout from the spray, and also a contribution from the canopy due to spray runoff from leaves. And that happens when you have a lot of spray applied to less or to limited leaf areas. So not every droplet that is captured remains there, because the leaves have their limited capacity to hold the spray. And so those have also been determined and have been factored into the computation. So the ground fallout would have the contribution from that leaf runoff as well. And then we have spray drift. This spray drift is a potential spray drift because the computations are only up to the edge of the orchard and not beyond the orchard. So I would say potential spray drift in that sense, or maybe to put it in a better sense, the computations are considered up to each single tree canopy. So it does not account for spray that misses the immediate canopy, meaning that the spray that misses the target could end up adding on to other canopies, but that additional spray amount, potential spray amount, is not included in the computations. It's not accounted for. So this would be what is actually estimated to be applied and captured by the canopy. Okay, so with that brief overview, let's look at the initial application scenario. So reading through it, you are planning to apply pesticide to a citrus orchard using a conventional air blast sprayer. And the recommendation says apply spray at 100 gallons per acre. This may not be what you're familiar with for citrus, but we'll be using this and developing understanding by changing different factors, so different variables. So don't worry about that too much. And so you plan to travel at least 2 miles per hour. The sprayer has 10 nozzles per side, but based on tree height, you would be using 8 nozzles per side. So we have 8 nozzles used instead of all the 10 nozzles, and this is the initial condition we are starting with. So we have 4 D4, D4 45, it could be D4, D4, and DC 45 upper nozzles, and then 4 D5 23 lower nozzles, and will be operated at 147 psi. So assume airflow rate of 42,000 CFM, and the orchard has 20 feet row spacing and 15 feet tree spacing within each row. There are 50 tree rows, each with 60 trees. Each with 60 trees per row, and no missing trees, meaning that the orchard has every single tree in place. So there is no missing tree. The trees are about 14 feet tall and 13 feet canopy diameter. Again, the canopy diameter on the tree spacing cannot be less than the canopy diameter. At worst, tree spacing can be equal to canopy diameter based on the fact that we have not included hedgerows. We have not accounted for hedgerows in the computation. So 13 feet canopy diameter and a medium foliage and skirt height of 1 foot. The weather conditions at the intended application time are temperature equal to 90 Fahrenheit, relative humidity is equal to 95%, and a wind, meaning wind speed, is 9 miles per hour. This is high. And I would also mention that the wind speed is accounted for in this way. In the calculations, we consider the worst case scenario. So wind direction relative to the direction of the spray is considered to be crosswind, meaning that wind speed, the wind is 90 degrees to the spray direction. So that is the worst case scenario. And so this 9 miles per hour and no rain is expected within 2 hours. This part may not be really necessary in this evaluation part because we are not using it directly, but this information can also be turned into the spray planning part to determine if it's appropriate time. But okay, so this is the we draw all the inputs from here and then run the simulation based on those inputs. And so this is showing the initial run giving us 57, 17, and 26 as in percentage of canopy deposition, ground fallout, and spray drift. Let's look at the other computations. Again, I'll say ignore this for now. The output per side display here, ignore it for now. This is the total volume applied. This is the total area covered. And this is the application rate. And then the number of trees sprayed based on the orchard condition information. So when you, in our second simulation run, we change temperature from 90 degrees Fahrenheit to 80 degrees Fahrenheit, and look at the difference, and we realize in this particular portion is giving the feedback as to what if the temperature was not 90 but 80. How does it affect the output here? And we realize in this particular case that it doesn't affect it that much. There would be the computations consider all those differences, but the impact on the on this what do you call it? The impact on the output is not really anything significant, so it does not show. But in another run, we have changed relative humidity from 95 to 80 to see what the results would be. And we see there is some slight impact on the total percentages, and that is there is also a decrease in canopy deposition, and this would be due to increased droplet evaporation because of the relative humidity that has decreased. And then ground fallout is decreasing from, ground fallout is decreasing from 17 to 16%. And then we have drift increasing because of the increased chance of evaporation. So we keep changing. Different things, different variables to see how it impacts the application. We see here we moved wind speed from 9 to 4 miles per hour, and then this leads to an improvement in the canopy deposition, and the ground fallout also increases. And the reason why ground fallout is increasing is because of the limited capacity of leaves capturing the spray. But the good thing is that, even though there isn't much increase, there seems to be, in terms of percentage, 2% increase in canopy deposition. The drift percentage has changed from 30% to 25%. So we can make decisions based on this. If we are considering a sensitive site, this could be a significant, improvement in drift. But then you can make all those changes to see what could, how you could improve your application. And then we have changed wind speed further to 2 miles per hour to see the impact. And we have, 56 becomes 57 on the canopy. And then drift is also reduced slightly, in the percentage. And then we are now looking at foliage density, changing from medium to high. So with every other thing remaining the same. Okay. So we see that because of the increased capacity of the canopy to capture the spray, canopy deposition moves from 57% to 80%. And this is just happening because in terms of the spray, it's the same amount of spray, same condition, but the canopy foliage density has changed. So there is more capture and more retention of the spray. And then that also tends to reduce the drift, but there is a slight increase in ground deposition. Anytime something like this is happening, mostly it's the contribution from the runoff from leaves, especially leaves that are closer to the sprayer. Then next we are changing the airflow rate from 42,000 CFM to 35,000 CFM to see the impact. And at high foliage density, that reduction in air power leads to a slight reduction in canopy deposition, but with slight increase in ground deposition. And again, this would be contribution from leaves, mostly leaves closer to the near side of the canopy. So with this, I would say go ahead and get onto the handout that was sent to you, and let's run through the simulations and use that to interact with the system. And so I decided to maintain some of the inputs from what I just went through for you. So the scenario is about the same, but this time it's your experience. So go ahead and make inputs, and just as yesterday, I would want you to complete this handout, include your name and license number, if applicable, and then you have the scenario in the first column, and in the next column you have your response that you put in. It's broken down into four sub columns, and AR is application rate, CD is canopy deposition, ground fallout, and spray drift. And these are the percentages. These are the values that you would be getting from the runs. These are the outputs that are shown, and this is the application rate that you'd find in the other variables. So go ahead and make these inputs into your system and run it. And once you're done running this, question A says, given the above information. So estimate, under your response in the last column, it says, estimate the application outcome, these values, okay, given the above information. Okay, so given the above information here, that is your initial simulation run. Once you run that and have the values, put those values in here. Okay, write them here in these sub columns or cells. And then B says, given 3 miles per hour ground speed, means that all this will remain as you have inputted, but then the ground speed that is given here as 2 miles per hour, this ground speed is going to change to 3 miles per hour in your second run. And then you run that simulation again and complete this with the values that you get from it. And while you go through this, I would want you to observe the changes that are happening as you are making all these changes in inputs. Look at how these are affecting the outputs. And I would want you, while you submit this, you definitely retain a copy for your comparison. And also, I told you I'll discuss part of it. So I would want you to complete this within the time that we are using for this session. This hands-on session is ending at 11 when we break. I would want to encourage that you complete this by 11. Okay, and I'm sitting here to look at your the charts, and then I would see if you're having questions from this exercise. I would address them. I would either reply with a chat, or I will rather just send you, just address it verbally. So. Yes, the question is about C. So what I want you to do when you are changing the inputs, every other thing that you have changed prior to that point remains the same. So when you change ground speed to 3 miles per hour in B, do not change it back to 2 miles per hour. Stay at 3 miles per hour. In C, you will only make this further change. That is change given for D445 lower nozzles. So you would make only this change while every other thing remains the same. And so sequentially, whatever you have changed prior to a particular point, just leave it as it is, and then change it. And as we do this, we would I want you to observe the changes in the outputs here. Yes, there is a question about the information provided in the scenario. I mentioned the question is about the output width and length. I mentioned that the air outlet width and length were based on the sprayer we use to generate the initial model. So leave these as they are by default. Do not change these values. They are by default. Just leave them and then work on the other values. So I just posted a chat message right now. If you are seeing bars, it means that you are working in, if you are seeing bars for the operating pressure, it means that you are working in metric units. For this exercise, please switch to English units. So the computations, the output will be based on the correct input. So PSI and bar are different units for operating pressure. So I hope this is clear.
Hello, Peter.
Yes.
So every stage, also the gallons per hour, the application rate changes. Do I need to set it to 100 every time or no?
No, you don't need to send it to 100. That you just need to run it and it will update by itself.
Okay, excellent. Thank you very much.
Do you mean the
application rate,
the output?
GPA?
No, you don't have to. You don't have to send it to 100. You can't change that one.
It will automatic, and that's okay.
It will change to a different value as you make the changes.
Great. Then thank you.
Okay.
Thank you. Bye.
You're welcome.
Okay.
I hope it's going well for everyone.
Hello, Peter.
Yes.
Maybe you covered, but what's the meaning of a minus spray drift?
What's the meaning of what?
Like I got for the spray drift in one case, like a negative number.
Yeah, negative value. Okay, so that is something I would address. I'll talk about that one when we do the discussion. So maybe I'll hold on with that one at this point.
Okay, thank you, Peter.
But it's okay, yeah, go ahead with that. So we still have 15 minutes until our break. And I'm not seeing questions, so assuming that it's going well for everyone. Still be looking out for any questions or interactions. Okay, we'll take the break at 11 o'clock. And I would say go ahead, please. And if you have not submitted your work, please go ahead and submit it. And then we'll take the break for 15 minutes. We will be back at 11:30 to finish up. We'll see you then. All right, so it's 11:16 right now, and I'm hoping that everyone is back from the break. So for the next 30 minutes, we would be discussing what we just went through. But before we do so, I would want to ask that if you have questions, you can send your questions to by chat, or you can unmute and speak to us. Julia, have you received all the worksheets back?
I believe so, yeah.
Okay, you have all of them back. Okay, so then we can discuss. So maybe I can go ahead and start the discussion, and any questions that come up along the way, I would address them. And if there are also any feedback from you, your interaction, you would please let me know. Okay, so we are starting we've started a wrap-up discussion and questions and answers. If you have outstanding questions, comments, and other interests, we can discuss that. So I'm going to start off with a discussion on the scenarios that we have been looking at. And I hope you had a good experience interacting with the application. We have this initial scenario with all the inputs provided that you need for all the inputs needed for the for the simulation. And so the first simulation run yields these values. The original target was to have 100 gallons per acre application rate, and this we started as something that was already provided, and all the information, all the other inputs were selected to yield the 100 gallons per acre. But if you, for instance, did not have that to start with, and you wanted to calibrate, then you would use the the target information, the target gallons per acre application rate, the speed that you intend to use, and then you will go and work it out to find the appropriate nozzles to use. Then you would come back to the evaluation part. Let me bring this up. So if, for instance, we are looking at, we have the target application rate that we want to use, and you don't have that information, you don't have the information, the right information to get the nozzle, then you would go to do the nozzle selection, and you would enter the information that you that is required to select the nozzle that you'd use to achieve that to achieve that application rate. Then you would come back to the evaluation and enter the and then select the nozzle type, the nozzle, the particular nozzle for the upper and lower sections. Okay, so what we have here, the results, this is what I'm expecting to have, 57% for canopy, then 17% for the ground fallout, and then 26% for the drift. And so we started with 2 miles per hour ground speed and yielded 100 gallons per acre application rate. Now in the next run, we changed the speed to 3 miles per hour with every other input remaining the same. And so given that scenario, the application rate, that output is going to move from 100 to 67%. And this is because we have increased speed, we have increased the land rate, as we discussed yesterday. By increasing speed, you have increased the land rate. So the denominator decreases, and with the numerator remaining the same, we end up with a reduced. So the denominator increases, but with the numerator remaining the same, so we end up with a reduced application rate. So the intent was not to really adjust this, but just to show how that affects the output. So in terms of percentage outcomes, so we have 62, 14, and then 24 for the canopy deposition, the ground fallout, and the drift. And we realized that in this case, the percentage decreased here, and the percentage increased here from 57 to 62. But the percentage is based on what was actually put out, not to say that this compares directly, but it is related to the total volume that was put out. So we can find what that volume is based on the total volume that is shown on the output. So we can see the changes, that the effect of the change, the ground speed change here. And while I'm doing this, please also check with what you submitted, your copy, and see if any questions come up in your mind, and you can bring that on board for us to. Okay, so we changed the four original D523 lower nozzles to D445 lower nozzles. We changed the size of the nozzle, but the number of nozzles remained the same. And so, given that the speed had previously changed, now we're able to increase the application rate because the nozzles are putting out more volume, more spray volume. So it moves to 89% for the application rate. And in terms of the outcome, the percentage-wise, the canopy deposition remains the same, but there is an increase in ground fallout and a decrease in the spray drift. The increase in ground fallout is, again, is due to runoff from the leaves. Anytime the spray volume is increased, there is a chance, depending on the canopy characteristics, there is a chance for there to be some runoff that is due to the limited capacity of the leaves. So then we changed the density, the foliage density from medium foliage as the starting setting. We changed that to high foliage density. And what that means is that now we have more leaves within the canopy to capture the spray. But that also provides an opportunity for for runoff. It means that because there's more leaves in the canopy, the tendency for all the leaves, all the spray to be captured, that is the spray targeted to the canopy to be captured, is high. That tendency is high. But at the same time, there's also the tendency for some increased runoff. So that is what is happening here that leads to a negative value of the spray drift. What it means is that there is a over estimation of the canopy deposition, and because of that overestimation, the spray drift was set to a negative value to compensate for that. And the reason is that the output from the spray, which is the canopy deposition, the ground fallout, and the spray drift, these are considered to be, to be a balanced system. So if one output increases, that goes at the expense of the others. So when there is an overestimation in one value, then the other is affected. So, and this happens mostly for the high foliage density. So it's one part that we would need to work on and adjust and be able to adjust the output so that we don't end up with a negative value. So this is something that will be improved in the new express system that we are developing. But currently, when you see a negative value, it tells you that there is some overestimation of the canopy density, canopy deposition due to spray runoff from leaves, and that is why the negative value is coming up. The next thing is, I think, yeah, this is supposed to be 3,500. 35,000, sorry. So this is, so for question E, we set the airflow rate to 35,000. Originally, it was rated at 42,000, and then we changed that to 35,000, meaning that the airflow rate has reduced. And in reducing it, the spray itself remains the same, in the spray volume and everything remains the same. So application rate remains the same as 89 gallons per acre, but then the canopy deposition is reduced to 84%, and then the ground deposition is reduced to 16%. So if you look at this, you realize that the overestimation could also be coming from the fast rate, the higher rate of dispersion that was coming from the higher airflow rate. But again, this can be adjusted. These values are more reasonable because the sprayer setup in the express system, the sprayer is set up such that the spray is adjusted to the canopy, the canopy size. So the assumption used is that there is no spray shooting above the canopy or shooting below the canopy. So this is reasonable: 84%, 16%, and 17%. And so if there is any increase from this to that, it should fall around, 84, 85 percent, rather than that 90 that we are seeing here, or maybe 83% rather than the 90 that we are seeing here. So if you look at the next one, we changed the nozzle size to a bigger nozzle size. We changed from D445 to D446 for both the lower and upper nozzles, meaning that we are maintaining a uniform spray. And that changed the application rate from 89 to 140 gallons per acre. So we see that by increasing the size, or by choosing a bigger size nozzle, we increase the application rate. In percentages, the canopy deposition is reduced at the expense of the ground fallout, and surely there is also some overestimation, slight overestimation in the canopy deposition here, and that is resulting in the negative value for the spray drift. But again, this will be addressed. So the next one, we have we changed back from high foliar density to medium foliar density. So every other thing remains the same. On the sprayer side, everything remains the same. The only change is in the targets. And so we see the application rate is remaining the same, but the canopy deposition has reduced. And this reduction is due to the fact that there is less number of leaves within the canopy. So, I mean, that reduced number of leaves means that more spray can escape the canopy. Less spray is captured, and for that matter, we see some big increase in spray drift. Okay, and there's slight change to the ground foliage. Sorry, the ground deposition. Sorry, ground fallout. Using different terms here. Okay, so these are reasonable, and next we changed from 8 nozzles, and now we have 9 open nozzles per side, meaning that we have opened 1 more nozzle, and that leads to a further increase in the application rate to 157. So we confirm that increasing the number of nozzles or adjusting the number of nozzles adjusts the application rate. the canopy position is reduced in this case, but again, it's a percentage of the total volume that is put out. But in terms of the percentage-wise, we have this reduction, and then there is an increase in the ground deposition or ground fallout, and there is also a slight increase in the spray drift. And this is the reason why we have more spray available, but the canopy remains the same. The canopy capacity, that's the total capacity, retention capacity, does not change. So mean that there is some ground fallout contribution from runoff from the leaves, but also there is opportunity for the spray drift to increase due to the fact that more spray is being applied here. And then we change further from 9 open nozzles per side to 9 open nozzles per side using D446 using D546. So further increase in the nozzle size, and that leads to an increase in the application rate from 157 to 220. The canopy deposition, percentage canopy deposition remains the same, but there is an increase in the ground fallout, also because we have now increased the spray, but the canopy characteristic remains the same. There is a reduction in the spray drift, and this reduction is also due to the fact that the higher nozzles or the larger nozzles are delivering larger droplet sizes, coarser droplet sizes. So those are less susceptible to drift, and that is being accounted for in the model. So there is this reduction in a percentage of drift. And then we changed the number of open nozzles from 9 to 10 open nozzles, but retained the size of nozzles, and we see what impact it also makes on the application rate. So it moves from 220 GPA to 245 GPA due to these changes. And the percentage canopy deposition becomes 55% instead of the 56 in the earlier run. But that is reduction is favoring the ground deposition, and the explanation is similar to my previous explanation that there is more spray. The canopy remains the same. There is more spray available, and so limited by the capacity of the leaves to retain the spray, there would be some runoff from the leaves that will contribute to the ground fallout. Okay, so I can go on running these ones, but I'll hold on and see if there are any questions coming out of these, or if there are any specific items that someone wants me to address, so that we can include that in this discussion. Okay, I'm looking at the chat and nothing is coming through. So I'll just stay on course and just run through these and just give the explanations. And if there are any feedback, I would appreciate those. All right, so now we change the operating pressure from the initial 147, yes, 147 PSI. Now we change that to 200 PSI. And we know that increasing the operating pressure will increase the sprayer output. So that goes to further increase the application rate here from 245 to 285. Tens of percentage outcomes. We have a reduction in the in canopy deposition, but there is some increase in the ground fallout without any effect on the spray drift, percentage spray drift. So this gives us an idea, some ideas as to, you know, what combination of settings would improve an application based on a previous run and so forth. So now we change the ground speed from 2 to 3 at B, but now we are keeping everything the same up to this point, and then changing back to 2 miles per hour. So the faster you travel, the lesser the application rate. So this, and vice versa, the slower you travel, the greater the application rate. So we see that effect here by changing the ground speed from 2 to 3 back to 2, we have 428. So it can go on and on, but I think our time is up, and I'll be looking forward to any feedback from you. We would be sending you an evaluation survey to complete, and for those of you also seeking the continuing education credits, you would have the opportunity to complete a final exam that is just based on what we have discussed, mostly from yesterday. And so you would complete that, and you need to score 70%, meaning that 7 out of 10. You have the opportunity to retake it if you miss it. So Julia, do you have any other thing to add to this?
No, I think you've got it. We'll be sending out that email with those instructions here shortly.
All right. Thank you very much. So thanks to all of you, and hope to interact with you in the near future. Thank you.
Hello, Peter. Do we need to leave the Zoom, the meeting, to get the PCA points? To do the exam?
Yes, you have to leave. Julia, can you respond to that?
Yes, you guys just received an email, or you should be receiving an email with instructions.
Yes,
it won't be on the Zoom, so you're free to go.
You are free to go now, yes.
Okay, have a great day. Thank you.
Thank you very much.
Bye-bye.